Problem 3 reads, the toggle switch consists of a cocking lever that is pinned to a fixed frame at A and held in place by a spring that is unstretched length of 200 millimeters, which is equal to 0.2 meters. Determine the magnitude of the resulting force A and the normal force on the peg B when the lever is in the position shown. So we have a lot of information here to dissect. First of all, we have this point here and this point here in which the spring exists. And because of the unstretched length is equal to 0.2 meters, if we know the full stretched length, then we could determine what the force is along this direction. But in order to get to that position, what we need to figure out is what is the hypotenuse of this supposed triangle. What we know so far is that from this point to point A, the distance is 300 millimeters, which is 0.3 meters. And then additional information is given. For example, B, which is located here, now exists along this other incline where the distance between A and B is 100 millimeters, and then the subsequent distance from B to this point of interest that we have is 300 millimeters, and we could convert these into meters, so we get 0.1 meter and we get 0.3 meter. Not only that, the information about from point A to this point of interest can be described as its own triangle with an angle given as 30 degrees here. This is 30 degrees, and we have the hypotenuse, which is essentially 0.4 meters along this way. Now, based on our triangle similarities, we could figure out that this side is going to be the sine of 30 degrees times 0.4 meters, and the adjacent side here will be cosine of that angle, so we have 0.4 meters times cosine of 30 degrees. And when I do the calculation, this is practically 0.2 meters because sine of 30 is 1/2, and we have 0.2 rad 3 meters for this side. So now when we look at the bigger triangle, this light blue triangle that I've drawn consists of this triangle. So let me redraw that here. This red line will be the extension from point A to one end of the spring. And the distances that we have is this is 0.3 meters. We have this is 0.2 rad 3 meters. And then this horizontal side will be 0.2 meters. What we can then do is figure out what is the hypotenuse of this big triangle. By taking the Pythagorean theorem, we get 0.2 meters squared plus 0.2 rad 3 plus 0.3 meters squared, and taking the square root of this. And my calculator tells me this is equal to 0.6766 meters. And of course, when we do our force from springs, we have force is equal to negative k delta x. This delta x is equal to the final stretch of the spring minus the initial stretch of the spring. And they tell you here that the unstretched length is 200 millimeters, so this unstretched length is going to be 0.2 millimeters, which we subtract from the value that we found, 0.6766 meters, and this will result in 0.4766 meters, which when we multiply to the spring constant, we will get the force. And there's no information about the spring constant. Actually, there is. There is information about the spring constant given here as k is equal to 5 newtons per meter. So force would be negative 5 newtons per meter times 0.4766 meters. And as a result, we get negative 2.383 newtons. So you might be wondering, well, why is this force negative? And to answer this question, recall that the spring was allowed to stretch along this axis. So what I'm going to do is I'm going to get this spring, and imagine if I had rotated so that the spring is now horizontal. So what we see is that this delta x allows this spring to stretch in the positive direction of this direction, and as a result, the force needs to be a restoring force going against this direction. So all that tells you is that from this point here, the force is going to be along the direction of the spring. So that leads us into the next part of the analysis, where at this point, along which the hypotenuse is modeled as a spring direction, we have this force of 2.383 newtons. And what we can find is that due to this, if we want to take the x and y components of this force, we have a negative x force component and we have a negative y force component because of how it's drawn here. Recall that we typically want the force to be positive in the x direction and positive in the y direction, in which both of these forces are not in that direction. Similarly, what I failed to do earlier was to mention that this addition of 0.2 rad 3 and 0.3 has a numeric value of 0.6466 meters, and the hypotenuse that we found was 0.6766. If you recall from one of the chapter 2 problems where we try to find the Cartesian vector notation, if we're given a triangle as such, where the hypotenuse is 0.6766, this adjacent side is 0.2 meters, and the opposite side is going to be 0.6466 meters. And along the same triangle, I'm trying to do a force analysis in which all I know is that the force here is 0.383 newtons. What I could find is that there's going to be similarities. And to figure that, I have to assume that this is some angle theta, and the cosine of this angle will be equal to 0.2 the adjacent side over 0.6766, and the sine of that angle will be 0.6466 divided by 0.6766. And notice that I didn't include the units here because I'm going to be dividing meters by meters. And as a result, this angle must be the same as this angle. So I have some sort of force x in this direction, which I know is negative. I have some force y, which is negative as well. I could figure out that the x component of the force due to the spring will be 2.383 newtons times cosine of theta. And the cosine of theta will be equal to this value. So I'll find that numerically. I'm multiplying the 2.383 newtons by 0.2 divided by 0.6766. And remember to include the negative because we want the positive x to be the positive direction. Similarly, the same thing can be applied for the force in the y direction. We get force in the y direction is equal to 2.383 newtons times sine of theta. And sine of theta we found just to be the opposite over the hypotenuse. So this will be 2.383 newtons times 0.6466 divided by 0.6766, and remember to make this a negative value. So now we have our forces in the x and forces in the y, and the numeric values will be negative 2.277 newtons. The force in the x direction will be negative 0.704 newtons. Now that we have these values, let's take another look at this cocking lever. The lever we have at this point where the spring is located, we determined that there is a force in the x direction and we have a force in the y direction. And notice that even though I put these forces in the positive x and y direction, numerically I know that these are going to be negative values from the calculation that I found. Although the direction is in the positive x-axis, the negative value tells me that it's going to be pointing towards the left, and for the y force it's going to be pointing down respectively. Then 300 millimeters down this lever, or 0.3 meters along this direction, I have point B as a peg, which only contributes a normal force in this direction. And at A, what I have is some unknown force, but this point A is located 100 millimeters away from this point B, or 0.1 meters away. And I assume that there is going to be some sort of resultant x force, which I will call AX, and a resultant y force, AY. Let's take a quick pause and realize why I drew the force B in this direction and why I had AX and AY here. If you look at the picture very carefully, what we see is that this point B essentially rests outside of the lever, and therefore the contact between the lever and this peg will only allow it to move in force B in that direction. Whereas point A is essentially within the lever, and at this fixed frame A, there's a reaction in order to keep this object in equilibrium. So now the part of analysis that we need to consider is this force B. What would be the x and y components? And all we know is that the lever is 30 degrees from the positive y-axis, and the force B is now perpendicular to this axis. So if we continue drawing that line and make it meet with the y-axis, we could determine what this angle needs to be. It must be complementary with this 30 degrees so that we have a right triangle here. And this is going to be 60 degrees. So I know that force B is essentially this side. And right now, this picture is a little deceptive because it says that the force B is one of the sides of the triangle and not the hypotenuse. So I need to manipulate this picture so that the force B is the hypotenuse, and I want to find what sort of relationship does it have with the y-axis. And this angle here is going to be the same angle given as 60 degrees. If this force needs to be the hypotenuse, then I'll make a right angle with the x and y axis, so I find that this resultant angle will be 30 degrees. So how do we find FBX, which I know will be moving in the x direction, and FBY, which is the force along the y direction? We could say FBX is going to be FB cosine of 30 degrees, and FBY is going to be equal to FB sine of 30 degrees. Or you could have said that FBX is equal to FB sine of 60 if we're going to use this angle. And as a result, I get FBX, which is moving now along the negative x-axis, will be the numeric value of FB times cosine of 30 degrees, and cosine of 30 is going to be radical 3 over 2. FBY, which is moving along the positive axis, will be equal to positive FB times sine of 30 degrees, which is equal to 1/2. So therefore, numerically what I found is that this FB I can now rewrite as having x and y components. Now, having represented all of these forces at those 3 points in terms of x and y components, naturally what I would do is I would find the sum of forces in the x direction and the sum of forces in the y direction. And what I'll do is I'll numerically leave it as these symbols. So the x component of the force due to the spring, which points downwards and to the left, or in other words, into the third quadrant, will be a negative value of 0.704 newtons. This is now followed with force Bx. Now, I know that force is going to be pointing towards the second quadrant, so therefore the x component of this force will be negative, as negative rad 3 over 2 FB. FB is the magnitude of the actual force in the correct direction, followed by this AX, and because AX I've defined it to be positive, I'll write plus AX, and this must be equal to 0. Now, the sum of forces in the y direction, I start off with the spring force, which is negative because it's actually pointing down, with negative 2.277 newtons, followed by a positive 1/2 force B with a positive AY, and this is equal to 0. So if you take a look at this, I have essentially 3 unknowns and 2 equations, and this is not enough equations for us to actually solve this system. So then we have to find the next one, which is the sum of moments. And recall that for sum of moments, anything that contributes to a counterclockwise spin we define as positive. And for a 2D system, moments are typically calculated by finding the lever arm and the force at a right angle of each other. And with any other angle, you have to use sine to essentially encompass that. And the trick that we're going to use here is look at this force B. The fact that this force B is already perpendicular with the lever arm direction simplifies it so that we necessarily did not have to do the x and y components of the force in order to solve for the moment summation. And how we start these sort of problems is we say, let's take the sum of moments at A. And we choose A because we have unknowns AY and we have unknowns AX, and we want to try to get rid of those sort of values. So the summation of moments at point A tells us that 0.1 meters away from this point, we have a force that's perpendicular. Now what we could do is we could try to figure out what is the x component of the lever arm times the y component of the force for B, and then similarly the y component of the distance and the x component of the force of B. But if it's already perpendicular, we could just simplify it as this lever arm times the force. And we can only do this for force B, but we will not be able to do that for the other spring force, which we'll see in just a little bit. So therefore, the moment at A is equal to 0.1 meters times FB. FB is unknown. And this will be in the counterclockwise position. So therefore, we see that it's going to be a positive moment. Now we're going to follow with this x component of the force and the y component of the force. And just to recap, let's actually look at point A, and I'll call this point S, which indicates the direction of the spring. This is our lever arm, where the angle here is given as 30 degrees based on the diagram here, and the distance between these 2 points will be 0.4 millimeters. So therefore, I know that the x component and the y component of this distance will be a function of this angle based on cosine or sine, which I know sine of 30 degrees, 0.4 will be this horizontal side, and 0.4 cosine of 30 degrees will be this vertical side. And at this point S, recall that we split up the forces in the x and y direction, so I have Fy here, and I have Fx here, and these are only given symbols to indicate the direction of the positive direction, but really I see that they are negative values, so they should be pointing in the opposite direction. And from this, let's now take the contribution of the moment when we take our analysis at point A. So let's start with this x component. So the x component, we know will have a negative value, but this x component of the force will be multiplied with the y component of the distance. So this will be 0.4 cosine of 30 degrees times fx, and fx is given as negative 704 newtons, 0.704 newtons. And we see that because the force is moving to the left and the distance is perpendicular to it, we can multiply them. But that will give us a positive moment. So therefore, I should write positive 0.704 newtons times this distance, counterclockwise for here. Now for the y component, what I see is that the y force is written as positive, but I see that it's negative. So according to the moment at point A, we will have a clockwise rotation, which means that this second moment due to this force will be a negative component. The value of the force is given as 2.277 newtons, and the distance, since we choose the y force, we must have the horizontal direction, which is 0.4 sine of 30 degrees. And this is going to be the moment that is calculated at A, and we find that this must be 0. So this equation will help you solve for FB, because we get FB is equal to 2.277 newtons times 0.4 sine of 30 degrees minus 0.4 cosine of 30 degrees times 0.704 newtons, all divided by 0.1 meters. And of course this will be in units of newtons. And once we have that, then what we can find is that we can turn this force in and figure out what is AX and what is AY. And this force B is equal to 2.02 newtons. Now we have ways to figure out what is AX and AY, because we know that AX, if I solve for AX by itself from this equation, this will be equal to 0.704 newtons plus rad 3 over 2 times FB, which we found to be 2.02 newtons. And then AY will be equal to 2.277 newtons minus 1/2 2.02 newtons. And of course, these are just the forces in the x and the y direction. So suppose that these are both positive values. I have AX this way, I have AY this way. To find the hypotenuse, which is FA, according to the notation given in the problem here, the force along A should be the magnitude of these, so AX squared plus AY squared. And that'll be your answer, which is given as 2.69 newtons. Thank you for watching.